Hi, my name is Steven. I'm an electrical engineer. I do board design and I help others with their board design. So today we are going to talk about TVS diodes, where I'm going to show you a schematic. I'm going to show you a layout. I'm going to show you simulations. I'm going to show you what to buy. So let's get to it. So depending on your case, you're going to have two different ways of doing this. So I've got option number one here is if you have a plastic case. Option number two here is if you have a metal case and you do have an actual chassis ground. So the first one right here, I've got my TVS diodes right here. So we're assuming on this first one, this is a 12 volt input. Line 2 just goes into microcontroller, random 1, doesn't matter what I picked. Line number 3 here is ground. So I put a fuse in here because I saw in a design at my work recently where they put the TVS diode after. I don't like doing that. I would consider it wrong because the name of the game for TVS diodes is to keep the parasitic inductance low. That's all you got to remember. That's the main thing you got to remember. Keep the parasitic inductance low. And even dumb it down just so anybody could understand. Grandma, keep the component close to the connector. That's all you need to do. That's the big thing. Spec your voltage, get it close to the connector. That is pretty much all you need to do. So, and I always do bidirectional TVS diodes. So I don't like unidirectional. Because in this scenario here, if there's a reverse polarity situation, well, the first thing to go is the diode. So, and I've seen unidirectional after the fuse. So, I mean, if you look around, it's a valid strategy for reverse polarity. I just don't like it. Fuses are meant to blow. These other components here are not. So I don't like that strategy for reverse polarity. So have your TVS diodes be doing TVS and transient voltage suppression. That ain't fusing. The T is for transient. Don't forget that. T is for transient. So I have a bolt cap up here. I've read that can seem to help, but as we'll see in the simulation, not really. I don't know if it's simulation or not. I have seen recommendations to put a cap in parallel with a TVS diode. In practice, not necessary. Does it help? Actually, a lot. And then I've seen to do a low pass filter is optional. I've seen that as listed as optional. So the only thing I've really seen in practice is just a resistor by itself. So termination resistor, that'll actually help quite a bit. But low pass filter, remember your ESD is going to be somewhere around 500 megahertz. So this low value cap here, that'll work for a lot of circuits, even relatively fast ones. Your cutoff, good stuff. Okay, so let's go look at chassis ground here. So still got the same fuse, bolt cap, RC filter, thing in parallel. But instead of going to ground, we go to chassis ground. If you've got metal on your case that you can tie to, this is preferred. Now this excess energy can be diverted away from your circuit. Here, it's got to go into your ground. That's not best practice to do it this way, but there are many, many, many designs where this works. So when I do a video about how to do a stack up, I'll just I will show you why I prefer to have two ground planes, even on a 4-layer board. That's not right now. What you'll also notice here, I've got an additional TVS diode, one from ground to chassis. So a lot of people don't do that, but it is best practice. I mean, think about it. You touch some connector that's connected to your board. Ground is not special. You're adding voltage. and current from, you're adding your ESD to this line, it needs to be diverted away. So that is why that's there. For my mounting holes, connected them all to chassis ground. Some people are going to go nuts and say, no, only do one. Star grounding. Guys, ESD is 500 megahertz. That's high impedance. Like, so a lot of people don't take the frequency content into consideration when they think about, you know, the loops, the ground loops. It's like the first question you got to say is, what frequencies are we talking about? So for how we tie ground to chassis, dude, that warrants its own video. The theory of doing this is that the resistor ties these together at DC. And then for anything crazy for high frequency, the capacitor will take care of. But I've also seen, I've heard motherboards, they won't have these at all. It'll be a direct tie. And there's layout tricks you can do. This warrants its own video as far as what to do. So now we've looked at a schematic, let's take a look at a layout. So this right here is our plastic case. Here's connector here. I just picked a random connector. So TVS diode is right here. So this, it's simple. Keep it close to the connector. Use big ass traces. This one right here, 80 mils. Huge. This is also 80 mils. So yeah, this one's longer than that. But because I did a wide trace, it will perform perfectly fine. This one here has the luxury of being right next to our ground pin. So yeah, just keep it close. Keep them wide. That's all you got to do. And then here's our optional RC circuit. It's close to the pin. So once again, close to the pin here, close to the connector here. Okay, I want to go back to schematic real quick. Close to the connector here, close to the pin here. So I do schematics in this fashion. That way, when I or somebody else is doing layout, they've got an idea of what I'm thinking about as far as part location. And it's just good practice. Let's go back to our layout here. Okay, so if you have a metal case, you're gonna should have a chassis ring all the way around. You might notice I didn't do here. Same thing about ground loops, man. Like, it's overblown, the concern about it. So I just didn't want to move these over. So, and if you get people whining at work, I don't want to make loops, just break the loop somewhere. So that's designed for politics, not engineering. Okay, so our TVS diodes are here and there. So, and this is a 4-pin connector. So our chassis ground is right there. And then our closest mounting hole is here. Okay, so then it goes through this trace, but it is not just one trace. The whole ring is on all layers of the board, and they are tied together by a shitload of vias. Now, KiCad doesn't give me a fancy way to evenly space these, but spacing of these does matter a bit due to frequencies, which means wavelengths and all that. Like 100 mils would be fine. So if you do have the luxury, you should place your mounting holes as close as you can. Well, a lot of designs, you will not have that luxury. But if you do, you need to plan out where your connectors are going to go and then where your mounting holes are going to go. Because this makes all the difference in the world. Because even though we've done all the techniques to lower this inductance, there's still quite a bit at the frequencies we are talking about. And here, I suppose I could have... I don't want to put them on. For my layers 2 and 3 are ground. So layer 4, I could have done this here also. Same thing, bunch of vias. And low inductance. That's the name of the game. So this is actually rather simple. The way... So this is one of those things. The best practices are the simplest practices. It's just... A lot of engineers out there just want to be cute, do their own thing. It's like, no, don't be cute. Don't try to be entertaining. Personally, I want my designs to be boring as hell. Boring works. Boring doesn't break. So I can go on a spiel on that for a while. So, okay, so we've got a schematic and we've got a layout. So I kind of want to do a... let's look at part selection. Let's scroll up here. These guys right here are my go-to. So for anything I would say is normal. Let's say what is not normal. USB, HDMI, any of those that need something with low capacitance. Because you're dealing with fast signals, you got to use something a little more specialty that's meant for those applications. But for normal stuff, this will work fine. So what I do like, 600 watt peak pulse power. Relatively big package, because we got to handle all that power. And then we got bidirectional. And then what we get, all the voltages I could ever want. That's why I go for these guys. I don't have to... I can just turn my brain off and get the right one. That's why I like these guys. So this is the one we picked. Bidirectional. So for our 12 volt one, we did this one. So it starts to break down a little bit above, which we like. Also, the math works out. You'll notice 20 times 30. There's your 600 watt. So for the rest of the stuff in your design, what I typically do, I look at this clamping voltage, and then for all my components downstream of that TVS diode, I make sure that they can handle this. It's just a foolproof way. So do you have to? I'd probably lean, maybe not. Just because, as we'll see in the simulation, this is around for such a short amount of time. That probably doesn't matter. Okay, one other thing you need to think about for these lower voltages here. Reverse leakage. This has actually got me on a product. Or not me. I'm the one who had to deal with it. So is this a big deal? No. Unless your device is battery powered, then yes. I can tell you in practice, when you actually measure it, it can be a lot. It can be way lower than what they have stated here. But well, when it comes to design, I'm going to rely on the data sheet. And probably worst case scenario in the data sheet. So I'd be relying on these numbers, even if in real world, it's way less. Okay. So now we looked at the data sheet and what's on here. Let me give it another look real quick. Make sure we didn't miss anything. Breakdown voltage, min and max. Okay, okay. Maximum clamping voltage, talked about that. I've never really done anything as far as temperature coefficients. We're not that picky. Okay, so let's go into a simulation. This is one of those you get what you pay for type things. It's a free program, so it is not without its quirks. So this is just an LT Spice. You can get it for free. So this right here is the standard for all this ESD stuff, you can look up the basics online. So, but point being, there's levels 1, 2, and 3. We tested, level 1 is 2 kV, level 2 is, 2 kV, 4 kV, 8 kV. I can tell you it worked for whatever reason. The compliance people, or we call them the EMI place, whatever, they test their ESD stuff at 4 kV. So that's a good starting point. So let's go on the right here. So this is for parasitics and to make simulation work. This is our actual TVS diode. So with some parasitic inductance, because that matters. This right here is capacitance because of our planes in our circuit board. Parasitic inductance just because of trace length. These are for those optional components to simulate low-pass filter. Bypass cap on our microcontroller, and then here's where we simulate the microcontroller pin. So I looked at a random one, and it said it's input resistance 5 ohms. So that's why we picked that. Every pin's going to have a little bit of parasitic capacitance. So then everything's going to have these diodes. If you look at a block diagram of a microcontroller pin, they will have these. So this one's for negative spikes. This one's for positive spikes. That's the one we care about. So now what we have on the screen here is this is power going through this Zener diode here, but for simulation purposes, that's all a TVS diode is. It's a specialized Zener. So, and then what we have, and then this red is measured right here for voltage, and then current going through there. Now, astute observers will notice that we have something like 50 watts going through here. The first question you might be asking, is that right? Simulation, man, I don't know. But I could believe it. Because look, it is such a short duration. So it should be able to handle a lot. And you know what? Even if simulation was wrong, I have seen numerous Arduinos have no circuit protection at all. And they all seem to last a year or two. So is the number itself right or wrong? I don't know, man. I haven't actually measured this type of stuff. But what I can tell you is whatever they do, even on your cheap microcontrollers, it works pretty well, man. A year or two, people constantly plugging and unplugging into a particular pin, and it still lasts a whole year or two. That's some good stuff, man. So that means if with the TVS diode here, you effectively don't have to worry about it. That's what we want. We want our designs we want to have some kind of goal, and we want to achieve the objective. And not have to worry, not have to go back. We just want it solved permanently. So, okay, what we're going to do here, this 3 nano henries. Oh my God, have I been saying nano? Nano henries. I've been saying farads for all these. Okay, so where we get these from, one of my favorite apps, Saturn PCB Design. So I just made up 50 mil wide trace. The height here, this is about what it would be on a 4-layer board. So 3.57 nanohenries per inch. So we're a little less than an inch. So this is still kind of far, but not crazy far. So let's say we did far though. Okay, remember, we're at somewhere around 400 watts for the TVS, somewhere around 50 for the actual pin. So we go to about 240, and then whatever's in between here, 75 watts. So yeah, even if you screw up your TVS diode, it's still gonna do stuff. It will still be effective, just not as effective. So that's all you, yeah, keep that in mind. Okay, so we're gonna keep this being kind of crappy. So here's what we're gonna do now. Let us simulate termination resistor. Damn. So that really helps a lot. So what's this at? Still 20, but that's a lot, man. Okay. Now let's do what we had in the schematic and go 330 picofarads. So that's kind of a small value, isn't it? Go 10 nano. Barely anything. So the RC filter will work. Okay, what if we, here, I want to keep the, I'm doing pico ohms. I want to keep the component in. I don't want to delete it. So I just want something so small it doesn't factor in. Ignore it. So, whoa, shit! So, don't worry about that. As I said, you get what you pay for. Simulations for a free program, sometimes not the best. So let's get that back in there. Spectacular. And notice, the better we do here means the more that actually goes through this TVS diode. So we're pretty much a little above the limit there. Not worried about it. I don't think I have ever seen a TVS diode actually fail. Yeah, these. Now I'm thinking about it. No, I don't think I've ever seen one actually fail. Yeah, I don't think I've heard about it. The only time I take that back. Fail under normal conditions. If your customer puts more voltage on here than the TVS diode is spec'd for, yeah, it's going to conduct and blow the component. But, you know, got to make sure your input voltages are in the manual to shield you from, I don't know, product liability, that type of thing. So, anyways, per simulation, keep this low, keep it close. You're not, if you can't keep it close, it happens. Just, it's best practice. So look at how big that goes now when you lower that. So we have gone through today schematic, layout, gone through a data sheet, and we've gone through some simulations. Guys, this is what I call a good day. So feel free to leave comments. If I forgot something, overlooked something, I always want to hear feedback. So I will catch you later in the next video. Have a good one.